Hi, I'm Younguk Yu, and I'm glad to present you our work curriculum fine-tuning of vision foundation model for medical image classification under neighbor noise. Let me start by introducing our paper. Our work focuses on learning with noise label using vision foundation models. Unlike previous methods which rely on CNN architectures trained from scratch, we concentrate on transformer-based vision foundation models such as DINO-V2. There are fundamental fine-tuning paradigms for vision foundation model in A and B, each with its advantage and disadvantage when trained on noise data. For example, linear probing performs better than the adapter approach when the noise rate is high, as it does not modify the pre-trained picture extractor and is therefore less vulnerable to memorizing noise labels. On the other hand, the adapter method outperforms linear probing when the noise rate is low, as it modifies the picture extractor to reduce the domain gap between the pre-trained and downstream datasets. Building on this insight, we propose a fine-tuning paradigm that combines one linear probing and two adapters to address noise labels during the training stage. So this illustration demonstrates our method, which uses three modules. The first is the linear probing module, which is the RPM, and the second one is the intermediate adapter module, so IAM, and the last one is the last adapter module, so last LAM. We train each module on a dataset filtered by other preceding module following a curriculum approach. Specifically, the LPM filters the dataset for the IAM, and the IAM subsequently filters the dataset for the LAM. So let's begin with the LPM. The motivation for using LPM comes from the fact that the linear probing is robust against the noise labels, allowing us to use our training samples to train LPM. After the training, we select samples where the LPM's prediction match the annotation. So these selected samples are considered as certain samples as they have a small loss. We assume that this filtered dataset has a low noise rate, though it contains only a limited number of samples since the accuracy of linear probing is relatively low. So the intermediate adapter module, IAM, is trained on the filtered dataset based on the fact that the adapter module outperforms linear probing when the noise rate is low. To obtain a larger and more accurate filtered dataset, we select samples from the entire dataset where the IAM's prediction match the annotations. And we assume that this second filtered dataset has no noise rate and contains a more number of samples compared to the first filter dataset. And finally, the LAM is trained using the second filter dataset, and only the LAM is used during the inference stage. So we evaluate our method on simulated noise label benchmark using 4 medical datasets with DINO-V2 and RAIN adapters. The average accuracy on clean test data for each dataset is shown in the table. Our method outperforms other methods, demonstrating that its effectiveness under noise labels by leveraging the pre-trained features of DINO-V2. Also, we utilize 4 backbones, including DINO-V1, MAE, DINO-V2, and biomedical clip, and 4 adapters, including visual prompt tuning, AdaptFormer, LoRa, and RAIN. Biomedic clip is clip-like model trained on the PMC 50 million dataset, which contains 50 million biomedical image text pairs collected from 4.4 million scientific articles. Our research demonstrates that our framework consistently helps build a robust classifier across different vision foundation models and adapters. To conclude, based on the insight that linear probing is robust to noise label samples, and adapters can generalize well with a few clean samples, we propose Cupid, curriculum fine-tuning paradigms for Vision Foundation model for multi-class medical image classifications. And QFIT utilized three modules, a linear probing module and two adapters to combat noise labels during training stage. Specifically, QFIT trains each module with filtered data in following order: linear probing, two intermediate adapter, and two last adapters. So experiments demonstrate that QFIT significantly improves the performance of VFM in the presence of noise labels for medical image classifications. Also, we validate that QFIT works well with various architectures, showing that the method is model agnostic. For more details, please visit our GitHub page. Thank you.